Earth's climate is chaotic and noisy.
Finding usable signals amidst all the noise can be challenging, be it predicting if it will rain, knowing which direction a hurricane will go, understanding the implications of melting Arctic ice, or identifying the impacts of human-induced climate warming.
Climate scientists use a range of tools to detect signals in the Earth's system.
In the Barnes group, we use machine learning, specifically neural networks, to sift through vast amounts of climate data and find predictable patterns in the noise. Neural networks learn from existing data by taking in information, processing it, and then making a prediction.
But is the prediction right? How did the network come to its conclusion? We use methods in explainable AI to answer these questions. These methods propagate information backwards through a network, starting with the prediction and deciphering the network's decision-making process along the way.
This allows us to not only gauge the trustworthiness of the network's decision, but also uncover predictable climate signals we didn't know were there. That is, we can learn new science.
The atmosphere is highly connected, and disturbances around the globe can impact your local weather. For example, an important disturbance in the tropical atmosphere, called the Madden-Julian Oscillation, or MJO, has worldwide impacts on weather everywhere, from Australia to the United States, the Atlantic Ocean, and beyond.
Other tropical climate phenomena, like El Nino or decadal oscillations in the Pacific Ocean, also influence global weather. Neural networks can learn these connections and correctly predict changes in these signals weeks or even years in advance.
We can also use neural networks to predict more local weather events that have a big impact where they occur, like rainfall in a particular region or information about a hurricane. Sometimes, we are interested in exploring how good neural network predictions are on their own. Other times, we can combine a neural network with another type of model, like a weather model or a global climate model. The neural network can then focus on improving or understanding where the weather model is wrong, or can take advantage of the large amount of data from climate models to learn more than they could from the real world alone.
To improve prediction skill, scientists often identify periods where a signal rises above the background noise of the atmosphere. These signals might not always be obvious, but we want to get as much information from them as we can. One way to use neural networks to identify these opportunities for good forecasts is by looking at how confident a particular neural network prediction is. When the network is confident in a prediction, it tends to also be a better prediction as well.
Machine learning can open new doors to understanding and predicting Earth's climate, both now and as the climate continues to change.
But even the best machine learning model is only as smart as the scientists designing it.
Building the future of climate science requires a diverse set of voices, a diverse set of backgrounds, interests, skills, and creative ideas.
This includes mathematics, physics, computer science, atmospheric science, meteorology, earth science, economics, sustainability, to name a few.
Working together, we can tackle some of the world's most pressing questions about Earth's climate.